On a clear night, far from traffic and billboards, the Milky Way does not look like a polite stripe on a classroom poster. It swells across the sky as a glowing wound of light, a pale river whose brightest stretch hangs low toward the horizon, near the constellation of Sagittarius. That river thickens into a hazy bulge, a crowded heart of stars, and through that heart run jagged black lanes, as if something has clawed the sky itself. To the first observers who truly paid attention, that bulge felt like the obvious center of everything. It rose and set with a slow, steady rhythm. It dominated the summer sky. It looked richer and denser than any other region of the band. Even when early telescopes turned toward it, the basic story held. More stars appeared, then more again, until the plates were drenched in overlapping points of light. Between them, the same dark cuts remained, like smoke trails frozen across a floodlit stage. Here is the paradox that has haunted astronomy for more than a century. We have always known where the Milky Way is brightest, yet, until very recently, we did not know what sits at its exact center. How can the most influential object in our galaxy be the least visible one? How can something heavy enough to steer hundreds of billions of stars hide so completely inside a glow we have stared at for thousands of years? Part of the answer lies between us and that bulge. The space along the galactic plane is not empty. It is filled with dust, tiny grains of carbon and rock and frozen molecules drifting between the stars. Each grain is nothing, smaller than the width of a hair. But taken together along the entire thickness of the disk, they form a veil. To the kind of light your eyes use, that veil is nearly opaque. It swallows blue light, soaks up red light, scatters everything into a brown fog. When you see photographs of the central Milky Way, you are looking at sunlight from other stars, filtered through this fog. The brightest place in the galaxy, as we see it, is not the actual center at all. It is the surface of the fog, lit from behind. What we call the galactic bulge is a projection, a bright curtain stretched across a darker, stranger room. Old observatories tried to punch through that curtain by gathering more light. Larger mirrors, longer exposures, higher in the mountains, above thicker layers of air. What they collected was not clarity but confusion. Millions of unresolved stars piled on top of one another, each one blurred by the atmosphere, each one dimmed and reddened by dust. If our galaxy had a true heart, it remained buried. The more we looked, the more the center resembled a crowded street where every sign shines at once and nothing stands out. From our position in the quiet suburbs of the Milky Way, that might have been acceptable. The sun orbits the center at a comfortable distance. Our sky is not filled with violent jets or searing arcs that cross half the firmament. Life here has the luxury to grow slowly, to breathe, to forget that it even lives in a galaxy. Why should it matter what lies in that distant, overexposed patch of Sagittarius, halfway around the disk? It matters because the gravity that shapes the Milky Way does not care about appearances. You cannot see a gravitational field, but you can feel where it leads. Every star in the galaxy is falling in slow motion around something. The spiral arms, the ring of gas, the boxy bulge, all of them move inside a deeper, invisible structure. If we want to understand why our galaxy has the shape it does, why stars formed where they did, why our sun follows its present path instead of some other, we have to know what sits at the center of that motion. For a long time, there was only speculation. Some suggested a dense swarm of stars crushed into a small volume. Others imagined exotic clusters of dark matter. A few dared to propose a single object of enormous mass, something so compact that light would struggle to escape its pull. The idea was simple, but brutal. Take millions of suns and compress them into a region not much larger than our own planetary system. Let gravity do the rest. The problem was proof. No matter how hard astronomers stared in visible light, nothing obvious emerged from the glare and haze. The center stayed stubbornly anonymous. The first real crack in the curtain did not come from a larger lens. It came from a different kind of sense altogether. To visible light, dust is almost a wall. To longer waves, it is more like fog in front of a radio tower. Think of it like this. If you stand in a smoky room, the beam from a flashlight will scatter and fade, but the warmth from a heater will still reach your skin. In space, radio waves act more like that warmth. They slip around dust grains instead of bouncing off them. When engineers began to map the sky with giant metal dishes, they saw a very different Milky Way. Instead of a smooth smear, the galaxy in radio is knotted and streaked. Along the plane, bright ridges mark regions of gas and energetic particles. Near Sagittarius, one spot burned hotter than the rest, a compact source that did not match any familiar star or nebula. Its position was not approximate. When the maps were refined, this strange point sat almost exactly where the center of the galaxy should be. It was a surprise born from irritation. Early radio work was driven by a practical problem: unwanted static in communication systems. The sky contributed to that static. A soft roar from above that changed as the Earth turned. Day after day, antenna beams swept across the heavens, and the noise rose and fell with them. That repeated pattern did not follow the sun. It followed the stars. Something in the direction of Sagittarius simply would not shut up. Name followed coordinate, as it often does. A label was attached that sounds more like a catalog entry than a threat. It describes a region, a constellation, a frequency. It does not carry any warning. Nothing about it tells you that this is the place where the geometry of space-time collapses inward. Nothing in that quiet phrase conveys the fact that we are dealing with a mass that dwarfs our sun by millions. A label alone is not enough. To turn a bright radio knot into an actual object, we needed to watch what it does to its surroundings. That meant finding stars close to the Galactic Center and tracking their paths over years and decades. Dust makes them invisible in ordinary light, but at slightly longer, infrared wavelengths, they can be seen. New instruments, built on tall mountains and equipped with moving mirrors that correct for the blur of the atmosphere, began to pierce the chaos. In those infrared images, the central region is not a calm swarm. It is a frantic dance. Points of light weave around a dark spot that itself never appears. Some stars trace wide, slow curves. Others dive in close and swing back out like stones on taut slings. One of them follows a path that loops around the unseen center in a time that fits inside a human career. In that brief span, its speed peaks at thousands of kilometers each second. No cluster of ordinary objects could hold it on such a tight leash without tearing itself apart. From these motions, from the shape of the orbits and the speeds involved, astronomers can weigh the invisible thing they circle. The answer is astonishingly precise. The compact object at the heart of the Milky Way carries the mass of roughly 4 million suns. Yet all of that weight is confined inside a region smaller than the orbit of Mercury. If it were a cluster of normal stars, their combined light would flood the core. It does not. If it were spread out clouds of dark matter, the orbits would show a different pattern. They do not. So what, then, can contain 4 million solar masses in such a tiny volume and remain so dim? What kind of object can push space and time around that aggressively while barely glowing above the background? And how do we live in a galaxy that depends on such an object for its structure, while remaining almost entirely unaffected by its moods out here in the suburbs? This is not just an abstract puzzle. In other galaxies, objects of similar mass announce themselves with terrifying clarity. They ignite disks of gas, launch jets that tear through intergalactic space, and beam radiation across vast distances. We see them as quasars, as active nuclei, as violent hearts that burn with a light brighter than their host galaxies combined. Our central object is the same type of creature, yet it behaves like a cold ember. It flickers now and then, but most of the time it barely breaks the silence. Is that quietness a permanent trait, or just a pause in a longer, more violent story. If the core once shone brighter, how did that change the chemistry of the galaxy? Did it bake nearby gas, strip atmospheres from early planets close to the center, reshape entire regions where stars might have formed? If it wakes again in the distant future, will that change the Milky Way we pass on to any descendants who survive long enough to see it? For now, its restraint is our opportunity. A central object in a low feeding state is easier to study than one wrapped in blinding beams. We can see the stars dance close by. We can listen to the soft murmur of gas swirling around it. We can attempt something almost absurd, building a virtual telescope the size of Earth to sketch the silhouette of its shadow. We live at the moment in history when our tools are just barely capable of confronting this thing directly. Yet even now, with all of that effort, we are still dealing with hints and outlines. We see how stars move, but not what lies beneath their orbits. We see a ring of radiolight, but not what lies inside. We can write equations for its horizon, but not for whatever, if anything, replaces the classical singularity in its core. Our knowledge has jumped from ignorance to contact, not to comfort. We have learned that the Milky Way has a monster at its center. We have not yet learned what that monster truly is. The next steps in this story will take us deeper. We will walk through the fog of dust that hides the center from our eyes and see what the galaxy looks like in heat and in radio. We will return to the first strange signal that should not have been there and follow it from an engineer's annoyance to a cosmic clue. We will circle the inner stars, feel the strain in their orbits, and watch as a portrait of the invisible mass gradually sharpens. We will then ask a harder question: whether this mass is a familiar type of black hole, or something even stranger. And finally, we will look far ahead, to the day when the heart of our galaxy no longer beats alone. If journeys like this help sharpen your view of the cosmos, please like and subscribe to the Quiet Universe channel. To follow that journey from the first pierced veil of dust to the full revelation of the Galactic Center, we begin by learning how we finally saw through the wall of light and dust that hides our own galaxy's true heart. The sky above a desert observatory at midnight looks strangely divided. Over the horizon, the Milky Way swells like a pale bridge, bright in its center and shredded at the edges by ragged black lanes. Those dark lanes appear peaceful from far away, drifting shapes overlaid on a soft glow. Up close, they are not peaceful at all. They are walls. They are structures of dust and cold grains thick enough to erase entire star fields from sight, turning the heart of our galaxy into a place we can sense only indirectly. Light tries to cross those lanes. It fails again and again. Blue light is scattered first, then green, then even the deep red glow of cooler stars. By the time that light reaches our telescopes, it has been muted into a reddish smear. If you could stand inside the bulge and look outward, the zone we inhabit would appear crisp, full of familiar constellations. But from our position, looking inward, the center seems like a bright cloth pulled over something we are not meant to witness. The problem is not distance alone. Even at 20,000 light-years, the sheer number of stars would betray the core if light could travel cleanly. The real problem is the fog. Interstellar dust clouds are sculpted from the ashes of old stars and the shrapnel of shattered comets. Each grain is ridiculously small, but together they form curtains stretching hundreds of light-years long. Trying to see through them with visible light is like trying to see through a bonfire by staring straight into the smoke. The more light you gather, the more the smoke reveals itself, rather than what lies behind it. Astronomers once believed that more power was the solution. Bigger telescopes, longer exposures, higher peaks. But increasing power only made the curtain look denser. Crowded star fields merged into a single sheet of brightness. Dark streaks widened into jagged rivers. Faint structures dissolved. It became clear that no amount of visible light would uncover the truth. The center of the Milky Way would remain hidden unless we learned to use a different sense. That necessity led to a shift in the way we listen to the universe. Instead of depending on light that dust could block, astronomers turned to wavelengths that slip around dust grains. The first attempts were crude. Large metal dishes pointed at the sky to diagnose interference in communication systems. At the time, the goal was to quiet the noise in radio lines, not decode the language of the galaxy. Yet inside the hiss, patterns began to appear. The background did not behave like terrestrial static. It changed as the sky turned. Some directions produced more noise than others, and one direction, toward the very region long hidden by dust, produced a signal stronger than expected. That was the first clue that the wall of dust was not hiding a random patch of stars. It was hiding something compact, something energetic, something that refused to show its face in visible light yet betrayed itself in radio. The revelation was unsettling because it suggested that our mental picture of the galaxy was incomplete. We had assumed the bulge was an overpopulated city block of aging stars, too dense to resolve. Now it seemed that a single object or structure in that region might be shouting through the fog. It is difficult to overstate how disruptive that realization was. For centuries, astronomy depended on visible light. Our eyes are tuned to it. Our early instruments magnified only what our eyes could already sense. To be told that the most important information about the Galactic Center was not in visible light at all felt like being told that the stars had been whispering in a language we never learned to hear. If we had been listening earlier, would we have mapped the heart of the Milky Way sooner? What else might the universe be saying in wavelengths we have not yet learned to detect? The shift to infrared brought a second transformation. Infrared light, longer and smoother than visible light, can slip through dust that blocks shorter wavelengths. When the first infrared surveys of the core were assembled, the pictures were shocking. The bulge was not a smooth haze. It was a tangled mass of crowded stars, extended clusters, and arcs of luminous gas. And in the very center of this chaos, a small dark void appeared. Not truly dark, because infrared is still a kind of light, but darker than the regions around it. A gravitational pit implied itself through absence. That absence did not shine. It did not glow. It did not flicker like a star. Instead, it distorted the traffic around it. Stars near the center drifted faster than those farther out. Some followed curves so tight that even a casual observer could see the imbalance. Those curves suggested a mass far greater than any normal cluster should contain, a mass that did not radiate, a mass that seemed tightly confined. Here, the contradiction deepened. If the dust wall was hiding a bright cluster, infrared should reveal it. But infrared saw no such cluster. If the dust was hiding a swarm of dark matter, the stars would move differently. They did not. If the dust was hiding a single collapsed object, the stars would gyrate around it with predictable speeds. They did. But if it truly was a collapsed object of enormous density, why was it so quiet? Why did it shine so faintly, barely above the background glow of gas and starlight? This silence became a clue of its own. Massive objects swallow everything around them, gas and dust included. As that material falls inward, it should heat and glow. In extreme cases, it should erupt with tremendous force. Yet the center of our galaxy showed little of this drama. Now and then, a brief flare rose in infrared and X-ray light, then faded. But overall, the region behaved like a furnace with no fire, a place where fuel vanished without producing much radiation. That quietness suggested that whatever lies behind the dust is not a star. It is not a cluster of stars. It is not a simple cloud of matter. It is something far more compact, a region where gravity folds space-time sharply. The dust wall, once an obstacle, now served as context. It was the wrapper around a mystery, not the mystery itself. To understand the dust, you must imagine how the galaxy builds it. When a massive star dies, it explodes outward in a spray of heavy elements. Those elements cool and bond into grains. The grains drift, collide, gather into filaments, collapse, and form the next generation of stars. The center of the Milky Way has seen many generations of star death and star birth. Its dust lanes are not passive. They are the residue of constant activity. That activity is what hides the very object that shapes the region. Infrared light gives us partial access. Radio waves give us another, but neither can completely reveal the core. The dust wall is not uniform. It is patchy, dynamic, and thick in unpredictable layers. In some directions, it absorbs more than in others. In certain infrared images, the center appears smeared as if the dust is trying to erase the last details. This makes the quest more challenging. Each technology that cuts through one layer reveals another. Even so, progress continued. Airborne observatories flew above part of the atmosphere and captured clean infrared spectra. Balloon missions drifted above the bulk of the water vapor that blocks heat from space. Orbiting telescopes went higher still and saw through the dust with clarity impossible from the ground. With each new vantage point, the picture sharpened. And yet, even with better views, one question kept returning. Why is the core so faint compared to the rest of the bulge? Why does the place with the greatest concentration of stars look less bright in the center than in the regions surrounding it? That odd brightness curve forced researchers to confront the possibility that the core is not dominated by starlight at all. Instead, it is dominated by gravity, and the gravitational center does not care about glowing. The clearer the image became, the more the dark regions stood out. It pulled stars into tight, fast orbits. It distorted the flows of gas. It carved an empty pocket where no stable star could survive. It behaved exactly like the deep well created by something extremely massive and extremely compact. And yet, the dust wall kept us at such a distance that direct identification was impossible. It was like seeing a whirlpool in a foggy ocean and knowing only the consequences, not the source. Why should an object that defines the motion of our entire galaxy be hidden behind such a wall? Why should the universe bury its most extreme structures under layers of dust that frustrate our earliest efforts to see? Perhaps the answer lies in the nature of galaxies themselves. They grow through collapse and merger. They collect material until the center becomes dense. That density forms a gravitational pit. Dust follows gravity. Light tries to escape. The struggle leaves a signature of both concealment and revelation. Standing beneath the bulge with the naked eye, you cannot know any of this. You can only see the misty glow. But now, with instruments tuned to other forms of light, we can peel back the first layers of the veil. We can see how the dust operates, how it absorbs, how it re-radiates. We can see the energy patterns beneath it. We can sense the careful choreography of stars trapped in the core's gravitational field. And once we know how to see through this wall, even partially, a new frontier opens. The next step is to listen to the signal that first slipped through this dusty barrier, a whisper from the Galactic Center that refused to fade no matter how often antennas turned away or toward it, or wars. Long before the sky became a map of wavelengths and satellites, it was a place of quiet assumption. Stars shone, planets reflected, nebulae glowed or faded. Everything seemed to follow patterns we could see with our own eyes. Then a new kind of listening began. Not with lenses or plates, but with metal towers built for a reason no one associated with the cosmos. These early antennas were meant to tame interference, the soft roar that plagued long-distance communication lines. Engineers traced the source of that roar across power stations, weather patterns, and faulty equipment. Yet part of the noise refused to behave. It followed the sky instead of the sun. Imagine a field of tall grass under a summer sky. In the center stands a rotating antenna, heavy, mechanical, turning its wide structure again and again to sample the air. Its purpose is simple: to find where static leaks into the signal chain. But every day, at the same angle to the stars, a faint hiss grows louder. When the antenna swings away, the hiss declines. The cycle repeats with night and day, but not with sunrise and sunset. Something beyond the earth is speaking, faintly, insistently. in a language made of static. This was the first hint that radio waves could reveal what visible light could not. The dust that blocked our view of the galactic center was nearly opaque to our eyes. But it was porous to radio. Waves hundreds of times longer than visible light could slide between dust grains, carrying information from regions buried beneath the haze. The antenna did not know it was looking into the heart of the Milky Way. But it was, and the signal it found should not have been there if the center were an ordinary collection of stars. The logic behind this is subtle. Stars emit radio waves, but they do so weakly compared to their visible light. A simple cluster of stars, even a crowded one, produces a kind of background murmur rather than a sharp peak. Dust clouds can glow in radio too, but not with the compact intensity that was recorded. The signal from the direction of Sagittarius was too narrow, too intense, and too stable. It was as if a single object in the middle of that chaos was humming with no regard for the light it failed to produce. To understand the shock of that discovery, you must picture the assumptions of the time. The Milky Way was still imagined as a colossal but fairly simple structure. A bright disk with a thicker hub and a smooth distribution of light. The center was crowded. Yes, but not special. Our sun orbited at a great distance and experienced no direct influence from whatever lay inside the bulge. The galaxy seemed passive, a background stage on which stars lived and died without being guided by anything in particular. The radio signal broke that illusion. If the center was simply a bright patch of many stars, why would it produce such a concentrated emission? What could generate a radio beacon from behind a wall of dust, thick enough to obscure even the brightest optical sources? Would the signal peak so sharply at a precise sky position rather than blending into the broader emission of the bulge? Astronomers began to map the radio sky. The first maps were rough, drawn by hand, derived from long sweeps of the antenna. But even in these crude diagrams, the center stood out as a compact knot of activity. That knot did not care about the fog of dust. It pierced straight through it. The sky had been hiding a powerful source in plain sight, but not in a form our eyes could detect. The years that followed turned the first crude detection into a global effort. New antennas were built with smoother dishes, more precise mounts, quieter receivers. Observatories learned to link far-flung telescopes together, combining their signals to sharpen the image of faint sources. Each improvement refined the view of the center. The knot of radio brightness became narrower, brighter, more defined. Whatever produced it was not extended across many light years. It came from a compact region, a tiny zone compared to the surrounding star fields. That compactness raised a disturbing possibility. If the source was small enough and bright enough in radio, it might be powered by something other than starlight, gas falling into a deep gravitational well, for example, can emit radio waves as it heats and spirals inward. A rapidly spinning object with strong magnetic fields can emit radio pulses. But there were no visible stars or clusters at that exact location. The dust wall should have revealed some trace of starlight filtered through it. Instead, there was silence in optical bands and a beacon in radio bands. This contradiction forced the question: what kind of object produces a radio voice without a visible body? What kind of structure sits behind a curtain of dust, shaped so compactly that city-sized regions outshine entire stellar neighborhoods? And why does this voice come from the place? Gravity insists, must be the center of the Milky Way. The implications did not stop with physics. They challenged a cultural instinct that had been with us for generations. We trusted what we could see. We built telescopes to extend our sight. We built observatories at high altitudes to purify it. But here was a crucial piece of the galaxy, a piece that determined the orbits of every star, hiding behind wavelengths our eyes were not designed to use. How many other structures might be concealed behind sensory blind spots we have not yet filled? And if the universe speaks across such a wide range of signals, how much of it are we still deaf to? As the radio maps improved, odd features appeared. Filaments rose from the central region like taut strings. They extended hundreds of light years, bright in radio but nearly invisible in other forms of light. These filaments suggested magnetic fields shaped by strong forces. Their orientation hinted at ordered motion. They were too aligned and too extensive to be explained by local star-forming regions. Something in the core was influencing them, guiding their structure in ways that demanded a powerful central source. The radio brightness also varied with frequency. Lower frequencies revealed broader structures, diffuse regions likely filled with warm electrons. Higher frequencies sharpened into a tight point, smaller and more intense. This layering was significant. It meant the core was not a uniform object. It was a hierarchy of processes, each dominating different wavelengths, but at the highest practical frequencies. The emission collapsed into a point so small that even arrays of telescopes spanning continents struggled to resolve it. The extreme compactness made one explanation rise above the rest: a collapsed object, a gravitational trap, something that could gather gas, compress it, heat it, and then let only a fraction of that energy escape. Not a normal star, not a cluster, something denser, darker, and far quieter in visible light. Even this would not have been enough if not for another clue. The position of the radio source matched the position astronomers expected for the dynamical center of the galaxy, the point around which all stars in the disk orbit. This alignment was too precise to ignore. The invisible location that shaped stellar orbits was the same location broadcasting radio waves with stubborn clarity. The puzzle pieces began to converge, even if the final picture remained out of reach. Still, doubts persisted. Some insisted the radio source might be a collection of unusual stars or a rare compact cluster. Others suggested exotic clouds or turbulent pockets of hot gas. All of these ideas needed one feature in common: a tight concentration of mass or energy. But as the mapping improved, each alternative failed one test or another. The emission was too compact, the frequency behavior too particular, the silence in optical bands too deep. Step by step, the center hollowed itself into a shape only one kind of object could fill. And yet, even as the evidence pointed toward a collapsed monster, the radio emission itself was odd. It did not roar like the emissions of active galactic nuclei in other galaxies. It murmured. It pulsed faintly. It rose and fell with short, unpredictable flares. Sometimes the source brightened several times brighter than normal within minutes. Then it faded back into the background. This flickering suggested pockets of gas falling inward suddenly, then disappearing. It was the signature of something feeding only reluctantly, taking in matter in small bites rather than steady streams. This behavior deepened the mystery. If the object was as massive as the orbital data later suggested, then it should have a strong influence on its surroundings. Yet the radio signal while firm, was not as overwhelming as those produced by more active beasts in distant galaxies. Something about our central object made it unusually quiet. It was a giant that seemed to be dozing. The dozing giant idea would gain strength in later chapters, once infrared observations revealed the frantic star motions near the core. But even before those discoveries, the radio signal stood as a stubborn fact. Something enormous was hiding behind the dust. Something compact and heavy, capable of generating intense radio waves without matching visible light. If the dust wall had been transparent from the beginning, the galaxy might have surrendered its secret sooner. Instead, the universe hid it behind a thick veil and whispered clues in a channel that only modern technology could hear. Standing at the base of an old radio dish, hearing the wind hum across the metal, it can be difficult to imagine that such equipment opened a route into the inner regions of the Milky Way. But every piece of progress began with an oddly persistent hiss that matched the turning of the sky rather than the rotation of the planet. The hiss was the galaxy speaking through its dust, offering a clue we almost ignored. And as we refined that clue into a precise map, we realized we had uncovered the first evidence of something that should not exist in its ordinary form. But a voice is not enough. To prove that the compact radio source was anchored by a massive object, we needed to watch what it did to the stars around it, and that required a new kind of vision entirely, one sharp enough to track the tightest orbits in the galaxy. In the heart of the Milky Way, there is no sunrise and no sunset, only a constant, bruised glow from stars packed so densely that their light blends into a single, trembling haze. Inside that glow, space is not gentle. It is tense. Gravity curls in tight spirals. Velocities stretch toward the limits of what matter can survive. The stars closest to the core do not drift like the sun. They race, weaving around an invisible point as if pulled along a narrow wire. If you could stand there, you would see motion everywhere, but nothing at the center that explains why everything else moves so fiercely. For a long time, this region was impossible to study. Dust swallowed visible light, leaving astronomers blind to the innermost stars. Only when infrared instruments matured did the real structure appear. Through that wavelength, the chaotic glow resolved into individual points, each marking a star speed tracing a path shaped by something deep and unseen, over years, then decades. Observatories gathered image after image of these points. They were not still. They shifted, curved, accelerated, and looped. The pattern was unmistakable. They were orbiting something tiny and overwhelmingly heavy. At first, the motions looked random. One star darted inward, then veered to the side. Another followed a disturbing trajectory that brought it close to the void and out again in a wide arc. But with enough data, these paths began to form coherent loops. Even the strangest courses could be described with simple gravitational curves. If the gravitational center was placed at a single spot with no visible body, to make so many stars obey that one anchor required something extraordinary. A cluster would blur, a cloud would spread, but a densely collapsed object, something incredibly compact, would hold fast. That is the beginning of the tightrope. These stars are not casually circling a faint object. They are performing high-speed turns around a center whose mass is millions of times that of the Sun. Their orbits are tight, fast, and violently curved. Several complete a loop within a human lifetime. One of them races in and out with a period of roughly 16 years. At its closest approach, it moves faster than any star in our part of the galaxy. No known cluster can exert such grip at such proximity without tearing itself apart. The only configuration that fits the evidence is a single, compact mass. Watching these stars over time feels like watching a dance that only gravity could choreograph. One star bends inward with a sharp turn, then sweeps back into deep space. Its motion so predictable that one could place a tiny mark on the frame and watch it return years later. Another dips dangerously close to the invisible point, accelerates to insane speeds, then flings outward again along a perfectly controlled arc. The dancers seem weightless, yet they are prisoners of a force so precise that it reveals its source not through light, but through the shapes of their paths. This is where contradiction becomes insight. If the center contained a cluster of smaller objects, their combined pull would drift over time. The orbits would wobble or smear. But these loops do not smear. They recur. They trace the same stages with each cycle. And if the source were extended, the stars would experience drag or differential pull. Instead, they accelerate as if falling around a point no larger than the smallest measurement allows. The physics leaves little room for alternatives. The mass is too large, the region too small, and the orbits too controlled. When astronomers plotted the speeds, the sharpest turn in the tightest orbit delivered a decisive blow to earlier ideas. At that moment of closest approach, the star in question exceeded several thousand kilometers per second. Only a gravitational field of immense strength could tolerate such velocity without ejecting the star from the galaxy entirely. But it did not eject. It swung around the invisible center with perfect obedience. That obedience is the signature of a gravitational pit deeper than anything found elsewhere in the Milky Way. The challenge was to measure the mass precisely. Over decades, researchers built models, refining their estimates with each improved observation. The result was astonishing. The invisible anchor at the core weighs about 4 million suns, and it occupies a space smaller than the orbit of Mercury. A cluster of stars with that mass would glow with unbearable brightness. A gas cloud would radiate across the spectrum. A dark matter concentration would produce a different orbital profile. But a collapsed object, extremely dense and extremely compact, would fit everything. If the galaxy were a vast atlas and the inner stars its cartographers, their orbits would mark the exact coordinates of the gravitational center. Their loops, when overlaid, point to the same near pinpoint. It is not merely a bright spot in radio maps. It is the rotational heart of the Milky Way. It sits in exactly the position where theory expects a supermassive collapsed object to reside. More importantly, it sits in the only place where the orbits make sense. The tightrope metaphor does not end with the stars themselves. Consider the distances involved. When the closest star swings past the core, it comes within an astronomical radius so small that, scaled to a human height, the star would pass inches from the center, while racing faster than any machine we can imagine. That motion pins the mass into a small enough region that almost no alternative explanations remain. If the object were a cluster, the star would plow through it or scatter. If it were a diffuse cloud, the star would slow and heat. Neither happens. It simply curves and escapes, as if grazing the brim of a shadow. These orbits also reveal another detail. The invisible object does not drift. It does not wander around the core. Its position is fixed within the measurement limits of the instruments. This is a strong clue that the mass is central in more than name. It is the actual pivot of the entire bulge. It is the anchor point for every rotating structure in the inner galaxy. Whatever sits there has been in place for billions of years, shaping the history of the Milky Way without revealing its appearance. When the tightest orbit was first completed with full precision, the scientific world felt the ground shift. The result was not only a triumph of observation, it was a collision between expectation and reality. The galaxy had been hiding a gravitational monster whose mass rivaled that of small galaxies. Yet it sat quietly, almost invisible, revealing itself only through the whirling of its closest companions. How often does the universe hide its most significant structures behind layers of dust and assumptions? There is another layer to this story. The orbits do not only trace classical gravitational curves, they show subtle shifts, small deviations predicted by the general theory of relativity. Space near the center is curved so strongly that the stars follow paths slightly different from those predicted by simple Newtonian gravity. These small corrections are faint, but they are present. They are the fingerprints of a compact object warping space-time. The more closely we examine the tightest loops, the more clearly these fingerprints appear. This behavior is not optional. Any object that warps space-time that strongly must be extraordinarily dense. The gravitational field is not spread over a large region. It is concentrated. A white dwarf cannot do this. A neutron star cannot do this. Even a hypothetical cluster of black holes would behave differently. What we see is consistent only with a single, enormous, collapsed object. Still, one might ask how this matters to a planet orbiting a star far from the core. It matters because the entire disk moves around this object. It matters because the formation of spiral arms, the flow of gas clouds, the shape of the bulge, and even the location where the sun formed are all linked to the gravitational structure of the center. If the mass were different, the galaxy would have evolved differently. Entire epochs of star formation would have shifted. Perhaps even the location of habitable zones in the disk would have changed. In other words, our existence is tied to a gravitational anchor we never see, yet the center remains quiet. If that mass were feeding vigorously, the inner galaxy would look like a torch. Jets would erupt, radiation would pour outward. The entire bulge would glow with furious intensity. Instead, most of the time it behaves like a dormant volcano. The stars show the shape of the pit. The radio signals show the whisper of gas near it. But the fire itself is dim. Why does a monster of 4 million suns rest in such calm states? What determines when it wakes and when it sleeps? These questions sharpen as our observations improve. Each new instrument allows us to watch the stellar tightrope more clearly. We can see the faintest turns and detect the smallest accelerations. We can measure the orbital planes and inclinations. These details allow us to test whether what lies beneath is as simple as a classical collapsed object or something more complex. The tests so far support the simple picture, but hints of deeper questions remain. When you look at stars dancing around a dark void, it is difficult not to ask what the void itself contains. The orbits reveal mass. They reveal location. They reveal stability, but they do not reveal the interior. They cannot tell us what lies beyond the point where light cannot escape. They cannot tell us if the interior collapses into a classical singularity or if something else prevents collapse. They cannot tell us how information behaves when trapped there. The stars, magnificent as they are, only map the edges of the abyss. To go deeper, we need to combine the tightrope evidence with sharper images of the region just outside the invisible boundary. We need to see the glow of gas that brushes the point of no return. We need to watch matter swirl at nearly the speed of light and trace the shadow it casts. Only then can we confirm that the dark object is what we think it is, or something stranger. This next step requires a telescope whose size is measured not in meters but in continents, a planet-spanning watchtower built from dishes scattered across the Earth, all synchronized to capture the faintest ring of light around the unseen core. In a universe filled with violent engines, the center of our galaxy behaves like an anomaly. Many galaxies advertise the fury of their hearts with beams that cut across intergalactic space. Some burn so brightly that they drown out the combined light of trillions of stars. Their cores tear gas into spirals of fire, launch jets that stretch for hundreds of thousands of light years, and roar in frequencies from radio to gamma rays. These are the active giants, monstrous in size and appetite. They do not hide. They flare. They burn. They announce themselves with overwhelming force. Against this cosmic backdrop, the center of the Milky Way seems strangely quiet. It is as if the galaxy shelters a giant that should be furious but is instead half asleep. The stars around it race at tremendous speeds, tracing the gravitational outline of a vast collapsed mass. The radio maps show knots of activity. Infrared flares rise and fall, yet the expected spectacle, the intense feeding frenzy of a fully awakened core, is missing. For an object weighing millions of suns, the overall glow is faint, a soft whisper rather than a shout. When astronomers compared our core to the monsters elsewhere in the universe, the contrast was startling. In distant galaxies, the most massive collapsed objects shine with power that defies simple intuition. Some contain billions of solar masses and feed with relentless hunger. Their accretion disks become cosmic lamps. Their jets thread the universe with thin, blazing wires. These giants do not rest, they burn steadily, marking the regions where matter collapses into maximum compactness. One of the most powerful examples in the known universe dwarfs everything we have measured in our own galaxy. Its central mass could swallow our local giant as if swallowing a grain of sand. If such objects are possible, why is ours so modest in its output? Why does a giant with 4 million solar masses simmer instead of blaze? This question is not merely comparative. It cuts to the heart of galactic evolution. Stars form when gas cools and collapses. Gas is influenced by central forces, shaped by gravity, compressed by shock waves. A furious central giant can halt star formation across a galaxy by blasting out gas, heating it, and pushing it beyond the reach of collapse. A quiet giant, however, allows the galaxy to cool and form stars in a more peaceful cycle. The calmness of our core might be one of the reasons the Milky Way has remained a stable environment for billions of years. But quiet does not mean harmless. At the center of our galaxy, the giant is not sleeping from weakness. It sleeps because, at this moment in cosmic time, it has little to feed on. The environment around it is relatively sparse. Gas that nears the core often fails to fall inward. Some of it is deflected. Some of it scatters. Some of it forms temporary streams. Only a small fraction spirals close enough to be heated. The rest drifts away. This makes the core seem starved, not inert. It is the hunger that keeps it dim. Every so often, something comes close enough to fall. When this happens, the core briefly wakes. The flares observed in infrared and X-ray arcs are small tremors of this awakening. They rise suddenly, then fade within hours. Their timing is irregular. Their intensity varies, but each one is a sign that the giant is capable of far more than it currently displays. If it ever encountered a sustained flow of material, its radiance would increase dramatically. The notion of a sleeping giant is not poetic exaggeration. The evidence of past activity is carved across the galaxy. High-energy bubbles extend thousands of light-years above and below the midplane. These structures hint at ancient outbursts, episodes when the core shone far more brightly. The fact that they exist suggests that our central giant has awakened before. It may awaken again. When it does, the Milky Way will not look the same. Imagine standing near the solar system during one of those ancient episodes. The sky might have shone with unfamiliar colors, illuminated by radiation from the core. Gas clouds across the inner galaxy would have boiled. Regions near the center would have been sculpted by violent winds. The arms of the galaxy would have carried the memory of that outburst through the slow spinning motion of the disk. Our serene view of the night sky would have been impossible. That history invites an unsettling question. Could life like ours have emerged if the core had remained active for longer periods? Would radiation from the center have sterilized regions far beyond the bulge? Would the delicate chemistry of early Earth have endured a galaxy bathed in periodic storms? The quiet state of the core may be a prerequisite for long-term habitability in the outer disk. We cannot prove it directly, but the idea is reasonable. Even a slight change in the activity level of the giant could alter conditions across tens of thousands of light-years. Despite its hunger and its history, the giant maintains a level of precision that demands attention. Even while dim, it exerts an influence strong enough to control the motions of entire star clusters. It confines the orbits of the inner stars to narrow ranges. It shapes the flow of gas spiraling through the bulge. Everything near the center responds to its presence, even though we barely see it. This mixture of invisibility and dominance shapes the mystery. How can something that determines the architecture of the galaxy hide behind such quiet output? One clue lies in the way the giant interacts with matter. Not all feeding is efficient. In some environments, gas plunges inward in steady streams, heating through friction and radiation. In others, magnetic fields disrupt the flow, forcing matter into chaotic spirals that emit light inefficiently. The core of the Milky Way seems to fall into the second category. Gas does not form a clean, bright disk. It forms a loose, unstable ring. Much of it escapes instead of falling. The small fraction that reaches the brink produces only modest light. This inefficiency is a gift. In more efficient regimes, the core would shine brilliantly and constantly. Instead, we witness only the dimmest glows. The relative silence allows us to study the region without being overwhelmed by radiation. It gives us access to the orbits and motions around the core. It gives us a view other galaxies cannot match. Most importantly, it offers a window into the behavior of a massive collapsed object when it rests. In that resting state, the giant holds many secrets. It hides its spin. It hides the texture of the space-time that surrounds it. It hides the details of how gas plunges inward. But it also reveals the outermost frame of those secrets. The stars circling at breakneck speeds provide the outline. The radio glow offers the trace. The quietness allows subtle features to stand out that would be drowned in stronger activity. Yet quiet giants do not remain quiet forever. In a galaxy filled with drifting gas and migrating stars, encounters are inevitable. A cloud might fall inward. A cluster might pass too close. A star might be torn apart. Any one of these events could feed the giant enough to wake it. If it wakes strongly, the Milky Way would change. Winds from the core could influence star-forming regions far away. Radiation could carve new shapes in the interstellar medium. the arms of the galaxy might shift their patterns. On longer timescales, the fate of the giant is tied to the fate of the Milky Way itself. Galaxies merge. When they do, their central collapsed objects spiral together. The future collision between our galaxy and its nearest large neighbor will bring the two giants face to face. Their dance will release energy in gravitational waves. The merger will reshape the structure of the resulting galaxy. In that distant future, the giant we study today will not remain solitary. It will become part of a larger heart. For now, the giant sleeps. It rules without spectacle, exerts power without brightness, and shapes the galaxy through a combination of presence and silence. We watch it through a veil of dust. We listen to its faint signals. We track the stars that dance at its edge. We learn from its restraint, knowing that behind the quiet lies potential energy that could, under the right conditions, erupt into cosmic fire. To prove the nature of this silent ruler, to see how close we can come to its edge without falling in ourselves, we must now turn to the instruments capable of capturing the faint glow that gathers just outside its point of no return. The closer we draw to the heart of the Milky Way, the more our familiar tools fail us. Ordinary telescopes, the ones that transformed our understanding of planets and nebula, collapse under the challenge. The core is too crowded, too dusty, too restless. Light bends, scatters, and shifts as pockets of gas swirl around the invisible center. Instead of clarity, we get distortions. Instead of a crisp image, we get a trembling blur. No mirror, no matter how large, can remove the turbulence of the atmosphere above it. No exposure time can freeze a structure that changes quickly from moment to moment. To see the unseeable, we had to reimagine what it meant to observe. The first breakthrough came from a simple truth. The Earth's atmosphere is alive. It ripples. It stirs. It acts like a layer of water above a lens. Anyone who has tried to photograph a moving candle through hot air knows the result. The flame jumps. It swims. It breaks into fragments. Stars near the Galactic Center behave the same way when seen through the atmosphere. Their positions jitter by tiny amounts that blur what should be precise motion. To correct this, astronomers built mirrors that could bend and flex dozens of times each second. These mirrors counteracted the distortion in real time, flattening a constantly shifting wavefront. The result was a new kind of vision, one capable of tracking stars near the invisible center with enough clarity to map their orbits. This technique, sometimes described in simple terms as reshaping a funhouse mirror back into a flat one, transformed ground-based astronomy. Suddenly, stars that once seemed lost in the glare appeared as individual points. Their motions became sharp enough to measure. Their loops around the center could be traced without drowning in blur. But even this was not enough to reveal the dark object itself. It only sharpened our view of the dancers, not the stage on which they performed. Beyond the atmosphere waited a different challenge. Even in perfect vacuum, the center was too faint and too variable to image easily. Gas near the invisible boundary glows in radio waves. But that glow is fleeting. It flickers as matter swirls, heats, cools, and plunges inward. Capturing it requires perfect timing and more resolution than any single telescope could provide. A single dish, even 1 kilometer across, cannot see detail at the scale required. The structures near the boundary are so small in angular size that, from Earth, they resemble a grain of sand seen from continents away. To overcome this, astronomers borrowed a concept from music, the idea that combining notes can produce harmonies richer than any single instrument. In radio astronomy, the same idea applies. Combining signals from multiple telescopes, widely separated across the Earth, produces a synthetic dish the size of the distance between them. This technique, called interferometry in technical circles, allows us to create an Earth-spanning observatory without having to build a dish that covers continents. The key is timing. Each telescope records incoming waves with exquisite precision, marking each crest and trough with an atomic clock. when signals from different telescopes are later compared. Slight differences in arrival times allow astronomers to reconstruct where the waves originated and how fine the structure is. The longer the baseline, the sharper the detail. Spread telescopes across deserts, mountaintops, and frozen plateaus and you create a planet-sized eye. This synthetic eye became the foundation of the most ambitious attempt to see the region just outside the invisible core. Multiple dishes were synchronized, positioned across continents, each tuned to collect radio waves at the same frequency. Together, they acted like one enormous instrument, precise enough to resolve features as small as the silhouette cast by a collapsed object on the glow around it. This silhouette, which appears as a dark center ringed by a faint halo, is not a direct photograph. It is the result of careful reconstruction, mapping interference patterns into an image. Yet the challenge deepened. The region around the core changes quickly. Gas swirls in irregular paths, rising and falling in brightness. Flares appear, then vanish. Structures shift within minutes. Imaging such a restless environment with a synthetic telescope that depends on stable signals pushes the limits of what radio astronomy can do. Observations must be long enough to gather sufficient data, yet short enough that the source does not change beyond recognition. Researchers had to develop new methods to sort and average the data, removing noise without erasing the signal itself. The outcome was more than a picture. It was a kind of shadow. The glow of hot electrons circling the core curved around the unseen object, creating a faint ring. Inside the ring was darkness, the imprint of a region from which no light can escape. The discovery was not only visual, it was geometric. It confirmed that the space-time around the core matches the warping predicted for an immensely dense object. The size of the ring, the brightness of the arc, the shape of the silhouette, all aligned with the enclosed mass measured by the dancing stars. Seeing that ring for the first time required an extraordinary level of coordination. Observatories on distant mountains aligned their dishes under skies that had to be perfectly clear. Planes of humidity and heat waves could distort the signals. Engineers braced for gusts and mechanical vibration. At high-altitude sites, where oxygen thins and temperatures drop, operators monitored the instruments with care. Each delay threatened the synchronized network. But when the conditions aligned, the Earth-spanning instrument opened its eye. The resulting image was modest in detail, yet immense in implication. The ring was blurred, trembling slightly due to the rapid changes near the core. But it existed. It matched what theory predicted for a collapsed mass of 4 million suns. It revealed the glow of matter skimming the brink of the point of no return. It showed, for the first time, that the center of our galaxy casts a shadow on the world around it. No cluster could do this. No cloud could create such a shape. Only a compact object, warping space-time so strongly that even light curves around it could produce the observed pattern. Even so, this was only the beginning. The image raised new questions. How does matter spiral inward before crossing the boundary? How chaotic is the flow? How much of the emission is driven by magnetic processes? How fast does the object spin? These questions require sharper images, finer timing, and observations across more wavelengths. To answer them, researchers plan to extend the synthetic telescope into space. A dish placed in orbit, linked with dishes on Earth, would increase the baseline to planetary scale and beyond. With such a configuration, the silhouette could be traced with far greater clarity. On the ground, improvements continued. Faster cameras, better frequency coverage, more stable timing systems, processing techniques that reduced the blur caused by rapid variability. Each advancement made it possible to glimpse detail that once disappeared into noise. The unseeable became less unseeable, not because it had changed, but because we had learned to listen to the chaotic whisper of a region beyond normal sight. Still, one truth remained. Even the best images cannot show what lies inside the boundary where light fails. The shadow reveals the edge, but not the interior. The ring shows where light bends, not where matter meets its final fate. to glimpse the nature of the core. To test whether it is a classical collapsed object or something stranger, we need to probe the structure of space-time near the horizon. This requires combining images with the orbits of stars, the timing of flares, and, eventually, the ripples in space-time generated by small companions falling inward. Before we follow those clues, we must confront the possibility that the shadow itself might mislead. Could some other object produce a similar ring? Could exotic structures mimic the silhouette? Could the universe hide a different kind of engine inside a shape we think we understand? To answer these questions, we have to walk into a deeper maze of theories, where the familiar model of collapse meets alternatives that stretch our imagination to its limits. The shadow at the center of our galaxy appears so convincing that it is easy to assume the case is closed. A massive, compact object bends light, sculpts a ring of emission, and anchors the frantic dance of nearby stars. The simplest explanation is a collapsed object with an event horizon, but science does not thrive on simplicity alone. It thrives on the pressure of alternatives, on theories that refuse to vanish until every possible test pushes them aside. And in the quiet zone around our galactic core lies a collection of such alternatives, each proposing a different kind of heart inside the darkness. The first alternative suggests a star made not of normal matter but of exotic fields. Instead of dense particles, this object would be a sphere of oscillating scalar waves, held together by gravity and the self-interaction of the field itself. In ordinary terms, it would be a star made of vibrations rather than atoms. These hypothetical objects, often imagined as giant balls of ultralight particles, could mimic some of the external properties of collapsed masses. They might even avoid forming a true horizon. If such a structure existed at the center, its interior would not collapse to a point. It would instead pulse, oscillate, and redistribute energy in ways a classical collapsed object cannot. The difficulty is matching this scenario to what we observe. The stars near the center orbit as if the gravitational mass is confined to a region not much larger than the smallest measurement tolerates. A boson sphere could imitate this behavior, but its surface would not be entirely dark. It might radiate weakly or reveal characteristic signatures of oscillation. Long-term monitoring has not revealed such patterns. The radio flickers near the core are too brief, too irregular, and too faint to match the steady pulse expected from such a structure. And the tightest orbits point to a mass even more compact than most boson configurations can support. Another alternative envisions a shell, a thin crust of exotic materials surrounding a nearly empty interior. In this view, collapse does not proceed all the way to a singularity. Instead, quantum pressure or some unknown interaction halts the collapse before it becomes infinite. The result is a hollow sphere, extremely dense at its boundary and nearly void inside. From afar, the gravitational field could resemble that of a collapsed object, but the surface, lacking a true event horizon, would reflect or scatter light in subtle ways. Some calculations suggest that as matter falls inward, it would hit the shell and generate a flash at the point where the inner boundary meets the infalling stream. This scenario invites a thought experiment. If a shell exists, where are the echoes of such impacts? Matter does fall inward at the center. Flares demonstrate brief heating, but none of the observed patterns resemble a clean surface strike. The emission is chaotic, shaped by magnetic processes and turbulence, rather than by the immediate conversion of kinetic energy into light expected from material hitting a rigid boundary. If a shell exists, it must be extraordinarily efficient at hiding its interactions. And the observed ring, which matches the expected silhouette of a classical horizon, would have to be coincidentally similar to the shadow produced by a non-reflective surface. There is also the idea of a tangle of strings, woven so densely that the interior is not empty but packed with the fundamental constituents of space-time. In this picture, the collapsed object is not a singularity but a knot of microscopic threads. The exterior would look almost identical to that of a classical collapsed mass, at least from far away. But near the boundary, the differences would become important. Instead of cleanly absorbing matter, the surface might process information, storing it in subtle changes in the network of threads. Light skimming the boundary might acquire tiny shifts in phase or polarization. Detecting such changes would require extraordinary instruments. We would need to see details in the emission ring at a level far beyond current capability. We would need to measure how the glow shifts over minutes as matter churns near the boundary. We would need to track the faintest ripples in the radio map, and we would need to understand turbulence in the gas well enough to distinguish intrinsic surface features from the noise of swirling plasma. None of these tasks are simple. They demand a new generation of telescopes and a deeper understanding of the chaotic plasma that lives near collapsed objects. Another possibility involves a wormhole throat, a passage leading to another region of space-time. If such a structure existed, the gravitational field around it could resemble that of a collapsed mass. The stars would still orbit the center. The radio glow might still form a ring. But instead of plunging into an interior, matter falling inward would approach a narrow throat. Depending on how the throat bends space-time, light could be bent more or less than predicted by a classical horizon. In rare cases, matter might even pass through, though most models predict instability and rapid collapse. The challenges here are even greater. A wormhole that remains open requires a form of support that seems incompatible with known physics. Even if such support exists, the geometry would introduce distortions in the shape of the shadow, possibly elongating or brightening certain regions. Observations so far show a ring shape consistent with a circular boundary, not the stretched or offset patterns expected from the throat of such a structure. If a wormhole sits at the center of the galaxy, it must disguise itself almost perfectly as a collapsed object. There is also speculation about dark matter concentrations. If dark matter could clump under extreme conditions, perhaps it could form a highly compact core. But for this to occur, dark matter would need interactions that current models do not provide. Simple gravitational attraction cannot compress dark matter to the required density. It passes through itself too easily. A compact clump would disperse. And even if a clump formed, it would not produce the deep gravitational well needed to bind the inner stars in such tight orbits. The orbits measured near the center rule out this idea with strong confidence. Despite the difficulties facing each alternative, the search continues because the universe often surprises us. Assumptions break. New physics appears when observations strain existing theories. The center of the Milky Way is a natural laboratory where gravity is strong enough to test the deepest ideas. It is a place where the boundary between known physics and speculation becomes thin. To turn speculation into understanding, we must rely on more than orbits and rings. We need independent methods to probe the region near the boundary. One such method involves tracking the precise timing of flares. These bursts of infrared and X-ray light originate from gas heated to extreme temperatures just outside the point of no return. As the gas orbits, the rising and falling brightness encodes information about the structure of space-time. If the central object has a surface, the pattern of flares might differ subtly from what we expect. If it has a throat or a reflective boundary, the timing of pulses might reveal echoes. So far, the flares match what we expect from matter orbiting a classical collapsed object, but the data remains sparse. A richer catalog of flares could expose effects now buried in noise. Another method awaits the future. As small, dense objects spiral inward, they emit gravitational waves. These waves carry the imprint of space-time curvature near the boundary. If we can detect such signals, they would provide a new way to measure the spin, mass distribution, and geometry of the central object. Space-based detectors could trace the gradual inspiral of small companions for years, building a detailed map of the region near the boundary. If the object is not a classical collapsed mass, the waves would reveal discrepancies. This technique is not yet available, but its promise is immense. A final possibility involves deeper imaging. Current images of the ring are blurred because the region evolves quickly. A clearer picture demands a network of telescopes even larger than the Earth, perhaps extending into orbit. With such a baseline, we could resolve substructures in the ring, distinguishing between theoretical models. A smooth ring would favor the classical picture. A ring with subtle asymmetries or unexpected brightness variations might hint at an exotic alternative. Each observation would act like a probe reaching into the unseen. But we must be cautious. Variations in the ring can also arise from turbulence in the gas, changes in magnetic fields, and uneven heating. Distinguishing structural features from noise requires both better data and better theoretical models. We must map not only the central object, but the plasma that surrounds it. Only then can we separate the true imprint of space-time from the chaos of matter spiraling inward. At this stage, every alternative faces a problem. None fit the data as cleanly as a collapsed object. The orbits of stars, the shadow shape, the scale of the ring, the timing of flares, and the faintness of the central emission all point toward a horizon rather than a surface. A shell would glow. A sphere of exotic waves would pulse. A wormhole would distort the ring. A dark matter clump would fail to bind the orbits. The simplest model remains the one with the strongest support. And yet, the search for alternatives remains valuable. It sharpens our tests. It reveals the assumptions in our models. It forces us to design instruments sensitive enough to catch the slightest deviation. Even if all alternatives fail, the failure teaches us something. It confirms that the central object behaves as expected under every stress we impose. But if one survives, if one deviates in a way no collapsed model can explain, then we will have found a crack in our understanding of gravity itself. Science does not close doors lightly. It narrows them through evidence. The center of the Milky Way has given us many clues, most align with a classical picture. Some remain ambiguous. The path forward demands new instruments, sharper images, and the patience to watch as the region evolves. The truth of the central object may rest on tiny details waiting to be revealed. To see those details, to confront the giant not only as an anchor but as an agent that sculpts entire galaxies, we must look beyond the boundary itself and explore how the heart of the Milky Way reshapes the cosmos around it. The center of our galaxy does not simply sit in silence while the rest of the Milky Way goes about its business. A massive heart, even a quiet one, leaves its signature on everything that surrounds it. The great lanes of gas that feed star formation, the architecture of the spiral arms, the thickness of the central bulge, and even the slow drift of the sun all reflect decisions made by gravity at the core. When an object carries the mass of millions of suns, it becomes a conductor shaping the entire symphony of the galaxy. From our distant position in the galactic suburbs, these influences can seem abstract. The sun follows a long orbit, completing one trip around the center in hundreds of millions of years. The view from Earth changes so slowly that generations pass without noticing any shift at all. But over cosmic spans, the center acts like the hub of a great wheel, guiding the paths of gas clouds, stirring the inner disk, and modulating where stars can form. If you zoom out far enough, the Milky Way arranges itself around the quiet giant. Even in slumber, it dictates the choreography. The most dramatic evidence of this influence appears in the structure of the bulge itself. The bulge is not a simple sphere of old stars. It is shaped like a thick bar, twisted slightly. Its proportions determined by billions of years of gravitational feedback. Simulations show that a massive central object stabilizes the innermost part of this bar. Without such an anchor, the bar could buckle or dissolve. The quiet giant keeps it firm. The stars that form loops within the bar do so under its steady pull. Their paths create a subtle glow that stretches across the central regions, a fossil record of the giant's long-term effect. Gas behaves even more dramatically. Clouds drifting toward the center encounter a tangled system of gravitational lanes. Some are compressed and forced to collapse into new stars. Others are stretched and torn apart. The giant influences these flows in several ways. Its pull generates tidal forces that can shear clouds into filaments. It can also steer gas into circular orbits where dense rings form. In environments like these, new stars emerge in waves. The core becomes not just a gravitational anchor, but a sculptor shaping the next generation of the galaxy's population. But the central influence is not constant. The giant's behavior switches depending on how much material it receives. When there is little gas to consume, it remains quiet. But if clouds or disrupted stars approach the core, the feeding rate increases. A sustained rise in feeding can launch powerful winds from the region around the boundary. These winds push outward, warming and thinning gas across thousands of light years. They can slow or halt star formation in those regions. Such events may be rare, but their effect is profound. A single strong episode can alter the galactic ecology for millions of years. Evidence of past outbursts is etched across the halo of the Milky Way. Large structures of hot gas extend far above and below the plane of the galaxy. They are shaped like elongated bubbles, glowing faintly in high-energy light. Their symmetry hints at a central eruption. If the quiet giant was the source, then it once unleashed enough energy to light the sky across great distances. The scars of that eruption remain visible. They are the shadow of a past era when the giant was not asleep. This raises a striking thought. If such an outburst occurred while life was evolving on Earth, would it have mattered? The distance from the core to the sun is vast, enough to shield us from the direct effects of radiation. But subtle influences could still propagate. Cosmic rays from a central flare might alter atmospheric chemistry. The outer disk might see a shift in star formation, affecting the distribution of young stars and the flow of gas. It is possible that events at the core have left fingerprints on the history of our region, even if faint. On even larger scales, the central object plays a role in shaping the galaxy's rotation curve. The motion of stars depends on both visible matter and the unseen mass that pervades the halo. The compact mass at the center anchors the innermost orbits. Stars deep in the bulge spin faster than those in the disk. The central giant ensures that the gradient of rotation is stable. Without it, the inner motions might become turbulent. Spiral patterns could shift or twist in unpredictable ways. The stability we observe is not accidental. It is maintained by the gravitational geometry of the giant. But the most dramatic rewriting of the Milky Way's future will not come from a flare or a wind. It will come from a collision. Our galaxy is drifting toward a large neighbor, and in the distant future, the two will merge. When that happens, the central giants of both galaxies will spiral together. Each orbit will tighten as energy radiates away in gravitational waves. The dance will end with a merger, forming a larger mass at the heart of the combined galaxy. This event will reshape the structure of the new system. Tidal forces will fling long streams of stars into wide arcs. Gas will be compressed in some regions, igniting new star formation, and stripped from others. The merger of the two giants will release enormous amounts of energy, creating ripples in the fabric of space-time that travel far beyond the galaxies themselves. If any civilization exists then, it may watch the night sky shift from spiral to chaotic blaze, then to a new stable form. The merged giant will rule the center of the transformed galaxy. This new heart will hold the mass of both old cores and will sculpt the structure of the future stellar population. Its influence will be more powerful than either of the individual giants that preceded it. The galaxy that forms will inherit its fate from a new central engine, one created through the fusion of ancient gravitational centers. Yet even before the far future arrives, the present quietness of our giant shapes our existence. A calm core radiates little. It does not flood the disk with destructive winds. It allows gas to cool and collapse into molecular clouds. It allows stellar nurseries to flourish. It maintains a background that supports stable orbits for billions of years. If the core had remained active for longer periods, the modern Milky Way might have been a harsher place. Perhaps the outer disk would have struggled to maintain the gentle conditions needed for life to grow. Our presence here may rely on the fact that the galactic heart chose calm over fury during the era that matters to us. These reflections lead to a deeper insight. The giant at the center of the Milky Way is not merely a gravitational sink. It is also a timekeeper. It sets the pace of change in the galaxy. It regulates periods of quiescence and periods of upheaval. It decides when waves of star formation rise and when they fall. It preserves the delicate balance between order and chaos in the inner regions. And through the long arc of cosmic time, its choices echo through the entire structure of the galaxy. Some of those choices remain hidden from us. We still do not know how fast the giant spins or how its spin affects the nearby gas. We do not know when it last experienced a major feeding episode or when the next one might occur. We do not know how its magnetic fields twist and evolve. These unknowns limit our power to predict future eruptions. But they also mark the frontier of a new kind of astronomy, one that combines light, motion, timing, and eventually gravitational waves into a single map of influence. This next map, still unfinished, will allow us to see the galactic heart not just as an invisible mass, but as an active agent. We will be able to watch how it manipulates its surroundings and how its history is written in the stars it shepherds. With sharper images, we will trace the flow of gas along magnetic filaments near the core. With better timing of flares, we will uncover patterns buried in the chaotic glow. With future detectors, we will listen to the spiraling paths of dense objects falling inward, hearing the shape of space-time itself. What we uncover may force us to rethink assumptions about how galaxies evolve. It may reveal that the central heart is even more involved in shaping the galaxy than we suspect. Or it may show that the Milky Way is unusual, that its quiet center has given rise to a unique environment on its outskirts. In either case, the central truth remains. The heart of our galaxy rewrites the Milky Way every day, not through brightness, but through gravitational orchestration. And now, having traced the role of the giant in shaping our galaxy, we can finally turn toward a question more philosophical than technical. A question about what it means for a civilization to live in a galaxy with such a heart, and what it means to notice that heart only at this moment in cosmic time. Stand outside on a moonless night, far from the hum of machines, and the Milky Way arches above you like a pale river suspended in silence. The soft glow looks gentle from here, a quiet decoration draped across the sky. Nothing in that view prepares you for the reality that behind the soft light lies a deep well of gravity, carved by a giant that has shaped the galaxy for billions of years. For most of human history, we did not know this. We traced constellations, charted the seasons, and imagined the heavens as a calm canopy. Only recently have we learned that there is a heart in that glow, and that it is not calm at all. Galaxies do not need permission to be violent. Their cores erupt, collapse, merge, and reshape themselves over spans of time far beyond anything we experience. Yet here we stand, on a planet orbiting an unremarkable star, living during a rare period when our own galactic heart rests. It rests long enough for oceans to form, for continents to rise, for life to learn to breathe, for our species to lift its eyes and begin asking questions. We exist in the quiet between storms. We build meaning in the pause. There is a humility in that realization. The forces that formed the Milky Way are not gentle. They did not nurture us. They simply created a stage on which, by chance, the conditions for life aligned. Our existence is a fortunate coincidence of distance, timing, and calm. If the center of our galaxy had chosen to feed more aggressively during Earth's early years, the outer disk might have become a harsher place. Radiation from the core could have altered star-forming regions or disrupted the chemistry of young atmospheres. Life as we know it might never have taken root. And yet, we are not simply bystanders. We are witnesses at a moment of revelation. For the first time, we can see the faint ring around the invisible giant. We can measure the orbits of the inner stars and trace the shape of the gravitational well. We can detect the whispers of flares near the boundary and glimpse the structure that hides inside the soft glow of the bulge. We may not understand the core completely, but we are beginning to perceive its outline. In cosmic terms, this ability is astonishing. A species that has existed for only a brief instant is claiming the right to map the heart of a galaxy. What does it mean for a civilization to awaken in the quiet era of its galactic home? How does a species define itself once it realizes that the heart of its galaxy is a silent giant? shaping everything around it without ever revealing its true form. This realization shifts our perspective. It reminds us that we are not central. We are not chosen. We are fortunate participants in a universe where calm pockets appear briefly between epochs of violence. It also raises a deeper idea. Perhaps every civilization across the cosmos emerges during such calm periods. Perhaps complex life requires not only a stable star and a suitable planet, but also a galaxy whose heart is resting. If true, then civilizations may be synchronized across cosmic time by the rhythms of their galactic cores. The giants sleep, and life arises. The giants wake, and the galaxy changes. The cycle repeats. This perspective reframes our sense of belonging. We are not merely inhabitants of the Milky Way. We are part of its momentary stillness. We depend on the balance between the silent giant at the center and the fragile worlds at the edges. We depend on a convergence of conditions that might not last forever. One day the calm may break. A new era of activity could rise from the center, or the merger with our neighboring galaxy could ignite the heart of the combined system with new fuel. Our future descendants, if any remain, will see a very different sky. Yet the transience of this calm does not diminish the beauty of the present. It enriches it. Meaning grows sharper when placed against the vast backdrop of cosmic processes. To exist at all, in a universe where most places are inhospitable, is remarkable. To exist in a galaxy whose heart currently sleeps is extraordinary. To exist at a time when we can observe that heart with instruments crafted from metal and light is something close to miraculous. Though it follows natural law, there is a quiet lesson embedded in this. Knowledge does not grant control. Understanding the giant does not let us command it. Yet understanding does grant perspective, and perspective grants a form of peace. We can look toward the center and see not only danger, but context. We can appreciate that our civilization is a local phenomenon inside a system shaped by forces far older and more powerful than ourselves. And still, we can find meaning here. We can choose curiosity instead of fear. As we refine our measurements and sharpen our images, we will deepen this perspective. Future instruments will detect the slow motion of dense objects spiraling into the giant. They will record the faintest whispers from the edge of the shadow. They will trace the spin of the heart and map the contours of space-time near the boundary. Each new discovery will illuminate a frontier we once thought unreachable. By the time the next century unfolds, the invisible heart may feel more familiar than some of the stars we see every night. And yet the most profound insight may not come from data, it may come from reflection. If everything in the galaxy, from the shape of the spiral arms to the path of our own sun, is influenced by a silent giant, then our existence is woven into a much larger story. We are a footnote in the long arc of our galaxy's evolution. We are observers who arrived just in time to notice the heart beating in the dark. A quiet thought emerges. Perhaps intelligence anywhere in the universe arises only during the pauses, the brief interludes when gravity's engines catch their breath. Perhaps the universe is filled with giants that swallow light and shape galaxies, and life is what happens in the shadows they leave behind. Perhaps every civilization is a spark that ignites during a restful breath in the cosmic cycle. Near the end of this reflection, one idea echoes with simple force. We live in a galaxy whose heart we barely remember to notice. The fact that we can notice it at all is a gift of timing, distance, and fragile peace. So we end with a question that outlives this chapter. If every galaxy grows around a dark heart, is intelligence in the universe simply what arises in the rare moments when those hearts fall quiet long enough for stars and questions to survive?